Hello, hello, my love. You are back here for more of how you say calculus, a B, a P, unit 4, the application of the derivative, huh? Well, let us start to go over the review notes for unit 4, applications of derivatives, for my AP Calc AB review course. Okay? Again, this is not the notes for Unit 4 in their entirety. This is the review of Unit 4. So it might not go over every single little thing, but it's going to go over the important things that you must remember if you want success on the AP exam. Let's get started. Okay. First thing is we have extreme values, okay? Our functions, our graphs, our equations will always have, or, most of the time should have some sort of extreme values. Sometimes there's not, but anyways, the extreme values are the mins and the maxes of the function. They are so easy to tell because on the graph, they are yep, that's okay, the mountaintops and the valleys. Meaning, mountaintop, that's easy to tell. That's a maximum right there. Okay, valley, it's easy to tell. That's a minimum right there. Okay, so we have maxes and mins. Easy to tell on the graph. But we can also find extreme values algebraically by setting f prime of x equal to 0. That means we just take our derivative, because that's what f prime is, and set it equal to 0. And anytime our derivative is equal to 0, we call that point on the graph. That value is where we have a critical point. A critical point is just where your derivative equals 0, okay? And your mins and maxes, if they occur, should happen at critical points. Not every critical point has a min and max, but if you have a min or a max, it's at a critical point, unless sometimes this is a graph that has endpoints. Sometimes an endpoint is higher than a mountaintop, or it's lower than a valley, okay? If there's arrowheads, you don't have to worry about it. But if they're endpoints, you always got to double check your endpoints, all right? So let me show you what this is. Now, find the mins and maxes and where they occur of the following function, y equals 1/3 x cubed plus 6x squared plus 27x. Now, they're asking us for two things here. Yeah, they're asking us for mins and maxes. Yeah, they are, but find the mins and maxes and then where they occur. Those are the two things, meaning the value of your mins and maxes, okay? Whenever I want the value, if I want to know what the mins and maxes actually are, that's your y coordinate, okay? If I want to know where they occur, that's your x coordinate, all right? So if I have a coordinate here, let's call it 2, 9, and that's a max value. The max is actually a value of 9. It happens to occur or is located at an x value of 2. All right? So for here, not only do they want us to find the mins and maxes, those are the y values, right? They want us to know where they occur. I need the x values for each one of those. All right? A lot of the times they'll ask you, what is the min or what is the max? That means you need the y value. Sometimes a question will say, find where the mins and maxes occur. That's it. They don't want to know what the value is. They just want to know where they occur. That means you only need the x value. In this problem, they're asking us for both pieces of information. All right? So based on our knowledge here, we know we need to find the critical points. We need to find where the first derivative is equal to 0. Okay? Power rule. 3 times 1/3. Well, that cancels. And then I subtract 1. So I end up with x squared. Okay? 2 times 6 is 12. And I subtract 1 from my 2. It becomes x to the 1. Plus 27. First derivative, I want to figure out, okay, I want to set it equal to 0 and solve for the x, because those values of x make the derivative equal to 0. And that tells me where my critical points are. And that tells me where all my possible mins and maxes can be. The location, because it's the x value. All right? So Factoring, it never goes away, people. Never, ever, 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 never, ever. All right? So, here we go. Booty cheek. T-bone. We'll do this one at a time. Two things, well, I know these are x's here, that multiply to 27 that add to 12. Plus 3, plus 9, okay? And if I solve each one of those factors, I set each one equal to 0 and solve, I know this factor, x would have to be negative 3, and this, x would have to be negative 9, okay? So, here we go. This value here and this value here, I know are critical points. How come? Because they make my first derivative equal to 0. So the million-dollar question is, how do I know if there's a min there? How do I know if there's a max there? But how do I know if it's a critical point, but there is no min or max there? Very easy, very simple. And it all has to do with the sign of your derivative. The derivative is the same thing as slope, right? So when x is negative 3 and x is negative 9, I have a slope of 0 because those make my derivative equal to 0, okay? So flat line, slope is 0. What happens if I have a positive slope leading up to my 0 and then a negative slope after it? Well, then that means this would have to be a max. Okay? What if I have a negative slope coming down to my 0 slope, then a positive slope going after it? Well, that would have to be a minimum. I mean, I can literally see it come down and up, minimum, valley, up, then down, hilltop, maximum. So what's a situation where I would have a slope of 0, but I not have a min or max? There's my slope of 0. What if it's positive, zeros, then keeps on going up? That is not a hilltop or a valley at all, okay? What if it goes down zeros, then keeps going down? That's not a hilltop or valley either. So what do we know? Okay, if the signs are the same of the derivative or slope on both sides of my 0, okay, see negative to negative, positive to positive, then there is no min or max. The signs have to change. I have to go from positive to negative, and I know I have a max. Or I have to go from negative to positive, then I have to, that tells me I have a minimum. So you say to yourself, well, I have my critical point. So how do I know if it's a positive slope to my critical point, then a negative slope, or vice versa? Well, I know what to do. I create a number line. All right? I'm going to put my two x values that give me my critical points. Negative 9 and negative 3. Right? Then I am going to put above that, on the top there, I'm going to put this is my derivative, or my slope. I know that my slope at those 2 points are equal to 0. All right? So now I'm just going to plug in other values that are not critical points and see if it's going to give me a positive slope or positive derivative value or a negative derivative value or a negative slope. Let me explain. Let's pick, I don't know, what about when x is 0? Not my slope, but my actual x value. That means I'm going to take my value of 0 and I'm actually going to plug it in to my derivative. Okay, so 0 squared is 0, plus 12 times 0, which is 0, plus 27. Well, when x is 0, my derivative would give me a positive 27. So it's a positive slope there. Okay, so I know that my slope over here has to be positive. It has to be a positive slope. All right, let's pick a number in between negative 3 and negative 9. Let's call it negative 5. All right, I'm going to throw negative 5 in for my x value. Okay, so now I've got negative 5 squared. That gives me 25, positive 25, plus 12 times negative 5, that's negative 60, plus 27. Okay, that's 52. If I combine those, minus 60, that's negative 8. So that's a negative value here, which means my slope goes down like this. That's a negative slope. Right here, you can visually tell this right here, it's going down, then up. That's a minimum. I mean, you can see it. It looks like a valley, doesn't it? Now let's try one more number. Let's try negative 10. Okay? And I'm going to put a negative 10 And for my x here, and then for my x here. All right? So I have negative 10 if I square it gives me a positive 100. 12 times negative 10 is negative 120 plus 27. If I add these two, I get 127 minus 120. That gives me a positive 27. No, I'll be okay. That gives me a positive 7. Okay, so that's positive, which means this slope is going up. It's positive, which means I know just by looking at my lines, I go up to down right here is a maximum. That definitely looks like a hilltop. So my coordinate for my maximum I know is negative 9 for the x. I don't know what the y is here. I know for my minimum, my x value is negative 3, but I don't know what my y value is. So right now I know the locations. My maximum happens at negative 9. I don't know what the maximum value is, but I know it happens at negative 9. And my minimum happens at the x value of negative 3. I do not know what the minimum is yet, but I know it happens at negative 3. So how do I find a coordinate? If I have an x and I need a y, I just go back to the original equation and I plug it in. Plug it into the original equation. Let's try to my negative 9. Let's throw my negative 9 in for each one of these x's. Okay? So if I throw a negative 9 in here, and here, and here. All right, I will do this on the calculator for the sake of time, although I already did this problem out. Yep, that is way too far, silly Billy. And I'm going to type it in my calculator just as it is on the board. Okay, alpha y equals enter 1/3. I'm going to have negative 9 cubed, right? Plus 6 times negative 9 squared. Plus 27 times negative 9. And I get 0. So I know the maximum is 0, and that it occurs when x is negative 9. Let's do the same thing for negative 3. Now, negative 3 I could probably do a little bit easier in my head, but what I'm going to do is I'm just going to go ahead and change all these negative 9s to negative 3s. And I hit enter, and I get negative 36, okay? So I know I have a minimum of negative 36 that occurs at x equals negative 3. Now, because I am the way I am, I like to answer the question based on the way it was asked. Okay, I would say there is a max of y equals 0 at x equals negative 9. This is a literal answer to the question. Isn't this an answer? I mean, it is, but I'm literally like responding to the question instead of just showing them a math quotation or notation, rather. Here it would have a minimum of y equals negative 36 at x equals negative 3. And there you go. Well, Mr. Magoo, it is done. Fantastic. You did good. We did good. That was a lot, but it's applications of derivatives. We're not just taking derivatives and stopping. Mean value theorem of derivatives. I see a lot on answer keys and on tests. People use MVT for mean value theorem. They do not write it out. They use MVT. Meaning, if they have to prove something and say that by using the mean value theorem, they will say, by using MVT, or by definition of MVT, whatever. So that was acceptable in my book. So if f of x, excuse me, is differentiable, and if something is differentiable, it has to be continuous as well. It has to be. Okay? If something is differentiable, okay, so if it is differentiable, it has to be continuous, okay? So if f of x is differentiable and continuous on the interval from a to b, then there exists a point C where, oh my goodness, the average slope between points x equal a and x equal b is equal to the derivative at some point x equals c in between a and b. Let me give you a visual, because I'm a visual learner, and I'm going to connect what I'm about to do visually with this stuff up here. Okay? with this stuff up here. I think we understand what this notation is, but this has nothing to do with the problem, so just pay attention to what I'm saying. If you want to write it down, you can, but make sure you leave room to solve this problem. All right? Let's take a look at a graph. If we have a graph here, okay, and I have a value here on the x, we'll call that a. And I have a value here on the x-axis, it's b. Remember, this is where x equals b. This is where x equals a. This is where we're getting these 2 points. All right? So we're getting those 2 points. Then the average slope between those 2 points has to equal the derivative at 1 point between them. So let's say this point is here, a. This point is here, b. Okay? The average slope between those two, that's this. Again, I need 2 points to find a slope, right? Change in y over change in x. I would go, that's a straight line. That's a slope. Let's say that's a slope of 3. I don't know. Okay? Then the average slope between those 2 points, the change in y over change in x, must equal the derivative of 1 point in between them somewhere at some x value, which equals c. Okay, now derivative is at 1 point. You need 2 sets of coordinates for this one, okay? So basically, if I have some graph that goes da ba boo ba doo 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 like that, okay? Then at some value c, I don't know where it is, yeah, ba doo, back together. Some value c between these, okay? The slope at the point, it's going to be the same, the tangent line. So let's say right here, the point right here is the same. Sorry, that's really bad. It's the same line. That means your point C would be right here. There has to exist some point. In order to get from A to B, if I were to draw a line from A to B, it has to, at some point, go straight, just like the slope. All right? So let's apply that algebraically, all right? And I'll leave our little graphic up here. In fact, oh my goodness gracious. Let's do this. Okay, yeah, let's move this all off to the side here. Bam. All right? So show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 2 to 0. First off, this is not a coordinate. This is saying from when x equals 0 to when x equals 2. So what are we going to have to do here? We are going to have to find the average slope between these 2 points and set it equal to the derivative of the function, okay, f prime of x, and solve for that x value and see where that happens, where they are the same. Okay, now the point being here is, how do I find the y value when x is 0? Well, I take 0 and I plug it into my function, right? So f of 0 is 0 squared, which is 0. That's the y value. Well, how do I find the x value? Or how do I find the y value when x is 2? Well, I plug 2 in. That would be 2 squared, which is 4. There you go. This is f of 2. So now I have 2 points to change in y over change in x. All right? Let's call this x2, or y2 and x2, x1 and y1, and let's find out the average slope. So it is 4 minus 0 over 2 minus 0. That's 4 over 2. The average slope between those 2 points is 2. This side is 2. That should equal the derivative of f of x. The derivative of x squared is 2x. So what value of x makes those 2 things the same? Well, let's divide by 2. Okay, 1. The value, or in this case, the c value right here, between 0 and 2 on the x-axis, that has the same slope as the straight line that connects 0 and 2 here, right? The same average value is the derivative of x squared when x is 1. That is it. All right, a lot of writing, a lot of fill in the blank stuff here. The graphs f prime of x, okay, When talking about graphs, the derivative, which is f prime of x, is the same thing as slope. And f double prime of x, or the second derivative, it represents concavity, means smiley faces or sad faces, the curvature, okay, of the graph, because not every graph is a straight line. So first derivative indicates slope of the graph of the original function, okay? So the slope is negative or downward, okay, when the first derivative is less than 0, or when it is negative, all right? The slope is positive or upward when my first derivative is greater than 0, or when the first derivative is positive. It's kind of the same thing, okay? Slope changes. It says at from, okay? Slope changes from positive to negative or negative to positive at critical points. And we just said that critical points is where f prime, or the derivative, is equal to 0, okay? Now, second derivative indicates, and it's right up on the top there in bold, concavity, okay? Concavity is negative, or a frown face, curves down, when f double prime, or the second derivative, is less than 0, or basically when it's negative, okay? Concavity is smiling or curving up, kind of, when f double prime, or second derivative, is greater than 0, which means it's positive. Now, when the first derivative is equal to 0, we call those critical points. Concavity changes from positive to negative, or negative to positive, at inflection points. This is where the second derivative is equal to 0. So when the first derivative is equal to 0, we call those critical points. I'm going to do this. I like my highlighter. Critical points. So when the first derivative is equal to 0. Okay? Inflection points is when the second derivative is equal to 0. And that's when you can tell, hey, is the graph changing, or the curve? I combined graph and curve and said GURV. GURV. Okay? Is the curvature of the function or graph changing from positive to negative? Is it curving up then down, or down then up, sad to happy, happy to sad, frowny to smiley, whatever you want to say? Inflection points. That's where the second derivative is equal to 0, okay? Find any extreme values, points of inflections, and sketch the graph x cubed minus 3x squared plus 4. We're going to do this all without a calculator, okay? So extreme values, those are mins and maxes. I need to find the critical point. That's when the first derivative is equal to 0. Okay? Points of inflection is the same thing as saying inflection point. That's concave up, concave down. I need inflection points. Okay? That's where the second derivative is equal to 0. Okay? So we need to go through here, and we need to find both of those, get those values, and just kind of plot points and get going, okay? So let's start, first of all, with our first derivative. Our equation, y. Y equals x cubed minus 3x squared plus 4. So I'm going to say y prime, the first derivative, is 3x squared minus 6x, okay? Set that equal to 0. What values of x? Well, let's start to factor. I can take a 3x out, GCF, greatest common factor. That will leave me x minus 2 equals 0. So I really have booty cheeks here. I'm going to T-bone. So x would have to equal 0, and x would have to equal 2. These are my critical points. These are the two places where possibly I have mins and maxes. Okay, so I'm going to put this on a number line, because remember, I have to have a positive slope to a negative slope. Okay, you don't have to write this down. I have to have a positive slope to a negative slope around my critical point, and that's a max. If I have a negative slope to a positive slope around my critical point, that's a minimum. Okay, so I need to create a number line. Boom, I'm going to put my two x values where I have critical points at 0 and at 2. And I know that my first derivative is equal to 0 when I use those two values. I'm going to pick numbers on the outside, in between and on the outside, and see if they're positive or negative values. All right? Let's start with, let's go green. We'll go with the number 1 right in between them. If I throw 1 into here, I end up with 3 minus 6. That is negative. That would give me negative 3. So my slope goes down between those 2 points. Let's pick a number to the right of 2. Let's pick 3. But mister, I want to pick 10. Go nuts. That'd be fine. You would end up with the same answer, okay? If I throw 3 in here, 3 squared is 9 times 3, that's 27. 3 times 6 is 18. 27 minus 18 is a positive 9. So I know I have a min at my x value of 2, okay, because it goes down, negative slope to positive slope. Let's pick here negative 1, okay? If I square negative 1, that gives me a positive 1 times 3 is positive 3. If I take negative 6 and multiply it times negative 1, that's positive 6. 3 plus 6 is positive 9. Positive slope. That means I have a max here. Okay, a max is 0, but I don't know what my y value is. I have a minimum at an x value of 2, but I don't know what the y value is. How do I find the y values for said x values? I take my x value of 0 here, and I plug it into my original equation. Zeros. 0 cubed is 0. 0 times anything is 0. 0 and 0 plus 4? That gives me 4. I have a maximum at the coordinate 0, 4. Let's do the same thing with the number 2, shall we? I'm going to throw 2. Okay, right now I need to find this value. What's my y value for x is 2? 2 cubed is 8. Okay, 2 squared is 4 times negative 3. That's negative 12. So right now I have 8 minus 12 plus 4. That is actually 0. And let me double check my work. 2 cubed is 8. 2 squared is 4 times 3, it's minus 12 plus 4. 8 and 4 is 12 minus 12 is 0. There we go. So far, so good. So if I want, I can start plotting these things here, but let's do that afterward. Right now, I know I have a max at 0, 4 and a min at 2, 0. All right, let's talk concavity. Second derivative. And then we'll start putting these things on the graph one at a time. Okay? Inflection points. I need to take the second derivative. That means I take the derivative of the first derivative, right? So my second derivative, power rule, that's going to give me 6x minus 6. I set it equal to 0. The only place that makes that equal to 0 is when x is 1. Okay, if I have to, let me add 6 to both sides. And I got 6x equals 6. If I divide by 6, x equals 1. This is my inflection point. Again, I'm going to do a number line here. Here's where x equals 1. That's where my second derivative is equal to 0. I'm going to pick values to the right and values to the left. Okay, meaning, let's pick x is 0. I'm going to put 0. Okay, I need to see where my second derivative, if it's positive or negative, see if it's a smiley face or sad face. So I'm going to take my 0, I'm going to plug it in here. 6 times 0 is 0, minus 6. That gives me a negative 6, so it's negative here. That means it's curving down like that. Okay? Now let's pick the number 2. Let's put 2 into our x value here. 6 times 2 is 12, minus 6 is positive 6. That means it's a happy face here. And you see my inflection point? That's at x equals 1, right? That's where I change from sad face to happy face, right at that point. So it's at the point 1, comma. How do I find my y value? When I have an x, I plug it into the original equation. All right? So I take my value of 1 and I plug it in here. 1 cubed is 1. Minus 3 times 1, that's minus 3. So 1 minus 3 plus 4. That would be 2. 2. This is the y value for my inflection point. Let's plot these things and see what happens, okay? Let's do this. I'm going to put my max should happen at 0, 4. 0, 1, 2, 3, 4, right there. 0, 4. That should be a mountaintop. That's a maximum, right? My minimum should be at 2, 0. 1, 2, that's right here. That should be my minimum, a valley, okay? Then at the point 1, I'll do that, let me do that in red. 1, 2, this is where I should change from sad to happy. All right, so what I'm going to do is, I've got points. I would like to see, okay, I'm going to do this in highlighter because I do everything in highlighter. I want to see what happens on this side. So I'm going to pick a point over here, and I'm going to pick a point over here. All right, so basically, no, that's not what it, basically, I'm going to find out, okay, what about when x is 3? This is. So if I throw a 3 in for my x's up here, okay, if I throw a 3 in for these x's, 3 cubed is 27, minus 3 times 3 squared is 9. 3 times 9 is 27 plus 4. Okay, these cancel, it's 4. So I have a coordinate, I have one more point at 3, 4. Okay, so 3, then 1, 2, 3, 4, right here. That's a point 3, 4. I'm just getting one more point outside my furthest right and furthest left point. Let's try -1 right here. Let's put a -1 in for these x's. See what I get. -1 cubed is -1. -1 squared is +1 times -3 is -3 plus 4. -4 plus 4 is 0. So -1, 0. These are additional points, okay? So what I've got to know is I've got a sad face that goes until my x value of 1, y value of 2. So I got a sad face until I hit here. So I've got a, oh my God, that's a sad face. Look how sad that is. See that? And that includes my maximum at 0, 4, okay? Now from there, I should switch from happy to sad, right there. And I should hit my minimum of 2, 0, and then come back up, boom, like that. There you go. That is a great graph. So here, let me do this here. My sad face, which hits my maximum, and then boom, switches right there. And let me go to some other color, pink. Now I start my happy face, and I hit my minimum right there. That's great, man. And you know, we're at the 33-minute mark. We've done a lot. And this is a good time to stop because when we continue, we're going to start related rates. And that can be tricky for some people. So this is a great place to stop. Part 1 is done, man. We're only going to need a second part to this, I guess, review 4. Unit 4 note series here. So it'll be a part 1, which we just did, and that'll be a part 2. Hit like, ring that bell, ring a ding 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 dong. And you know, if you want to share with some people who need help with calculus, I mean, that's what I'm here for, man. All right, I will see you guys later for part 2. See ya.